It's 2:03. I'm not going to say anything about the doorbell and curse myself. Happy Garbage Day, everyone. Happy Halloween hangover, complete with candy. I got to tell you, Saturday mornings, my son is in a bowling league for youth in Iowa City. And so the kids were a wreck on Saturday morning bowling. Like, they just looked so tired. My son's friend actually came up and asked his dad, "Can we just go home? I'm too tired for this." So the other thing that was entertaining about being out on a Saturday morning after Halloween was, you're familiar with the expression, the walk of shame, when you wear last night's clothes home the next day. The Halloween walk of shame is especially entertaining. I saw an undergrad who's like a 6-foot tall dude in a bunny costume, pink bunny costume, just walking down the street. Other people in various stages of costume disarray and, makeup smearing and all this stuff. So entertaining. You could picture it, right? The other side is less pretty, but but that's okay. We've got lots of leftover candy. Keep passing it around. I'm going to keep bringing it until it's out of my cupboard. So we're just going to have candy for the next month or so. That's what's going to happen. Yeah. I'm dead serious. I have more at home. You take as much as you want. Take some for your roommates or your partners or whomever likes candy. Get on their good list. Let's see, nothing was due yesterday. You get a little break. The next thing is going to be a formative assessment, and it doesn't exist yet. I'm trying to decide what questions I want to ask, and that's partially dictated by how far we get today. So it's in progress. I forget whose turn is it, Hillary or Michael next time? I think it might be. It's Hillary, okay. Yes, Hillary's kids are home today, too. Hi. Math is still money, kiddo. I told him that once.
Me literally at parent-teacher conferences last week was like, math plus coding equals money.
My work here is done. I believe the children are our future. All right, let's see, where was I? Oh yes, formative assessment is the next thing. Not done yet. I will let you know as soon as that is available, and I will send it to the TAs to test to make sure that it is less confusing. And the next thing will be homework 4. That is also being worked on by the TAs, and that should be open by the end of the week. That'll be due the 17th before Thanksgiving. That one requires a lot less coding than usual. I will just tell you that. Okay, it's meant to be sort of a review, recap sort of thing, and most of the answers are going to be just found straight in the output. That's the good news. The bad news is there's going to be like 5 models. So it's longer. So trade-off. But don't want to scare anybody. It will be fine. I put up this picture, this lovely little Venn diagram to remind us about what we started talking about last week. So we're changing gears from models that have just one conceptual predictor that may take more than one slope to models that combine different predictors on purpose to assess their unique contribution. This is slide 10. So that requires understanding not just how the predictor variables relate to the outcome that we're trying to make, but also how the predictors relate to each other. And the bottom line is that optimally, you want your predictors to be uncorrelated with each other. Like, that's when they will have the best chance of contributing and showing what they're capable of, so to speak. To the extent that the predictors overlap, they have less room to show a unique contribution, and that unique contribution is going to be more inconsistent across samples. So that's something that you would want to do some detective work ahead of time to figure out how related your predictors are to ensure that there's not a whole lot of redundancy, at least to avoid it to the extent that you can. So in these sorts of diagrams here, the idea is that we are labeling the parts of the variable that are unique with respect to its relationship with the outcome. So A is referring to the part of x1 that's related to y that is unrelated to the other predictor x2. B is the opposite of that. C is where they're both related to y, and so we can't say who's responsible for that contribution to the model. So we don't try to say that. So the R-square for the model would be a function of all 3 areas. What x1 brings to the table uniquely, what x2 brings to the table, and what they share. But in terms of what the slopes mean, the slope for x1 would only reflect the A contribution, and the slope for x2 would only reflect B. So we have both general utility that takes the common part into account and specific utility that just focuses on each variable. That's the big picture. Then we started talking about effect sizes. This is a whole thing, right? Should we talk about that a little bit more? I should assume you don't have perfect recall of something that happened 5 days ago, especially after a Halloween hangover. The candy kind, of course. All right, let me start here. This is slide 19. So we need effect sizes for various reasons. They are used to describe how strong a relationship is in a metric that people understand readily without needing to know the units. So if I tell you that a correlation is 0.3, you know that is on the smaller side of the correlation scale. If I tell you that a D is 0.5, that means a half a standard deviation mean difference between two groups. So you don't have to know what the scale of the predictor or the outcomes is to understand what those numbers mean. They're also, effect sizes are useful in doing meta-analyses and predicting power in future research. The question is which one and in which metric? So this is, to me, unnecessarily confusing because of differences in terminology. Eta and R are the same thing. So you will see in this context, effect size is called eta and eta squared, when what they really mean is R and R squared. So don't let that throw you. That's not a distinction. Whether you have, partial or semi-partial, I think is the primary distinction that's important. And then whether within each of those you're talking about an R metric, in which case you can have it be positive or negative as a relationship index, or R square, which is only positive. The tempting thing with the squared version is to use these statistics, these effect sizes, to talk about variance explained. Anytime you're in an R squared metric, people want to start using those words. It's not really valid to do that for the partial family, but it is for the semi-partial. So the approach that I'm going to recommend is like a hybrid of what's possible here in terms of which ones you would report and for what purposes. So I'm not going to use all of them, but I am going to use a couple different ones for different reasons. And if you are reporting adjusted R square instead to try and correct for low sample sizes, then the eta turns into something called omega instead. So we had a couple. I don't like standardized slopes. Here are the reasons why. We talked about those. Anybody read the blog post that I recommended? It's a good one. It's a short one. I recommend it. So semi-partial is the idea of relative to the total variance. What is this effect responsible for? And for this one, the squared version makes a lot of intuitive sense. What it's telling you is what that variable's contribution is to the R square of the model. So for instance, if the R square for a model is 0.25 and a semi-partial R square is 0.1, that means that predictor did 10% of the explaining out of 25% total. It's directly intuitive, like how much did this one do towards your total R square? So if you want to talk about the contribution to the R square, semi-partial is the way to go for that. It has the advantage that it's not unduly influenced by the number of other predictors you stick in the model because it's relative to total, which always stays the same. Partial is relative to residual only, and that's the big difference, is that this denominator is a moving target. So conceptually, it represents the contribution above and beyond the residual or above and beyond what the other predictors did not yet get that's left in the residual. And if you're like, how do I put those words in a paper and have them make sense? Yes, that's a very difficult concept. It's the R square for what's left. And it does not have any direct relation to the model R square. So that's why I do not recommend partial R squares in most cases, is because people want to talk about it as a contribution to the model R square, and it's just not. It's relative to a different denominator. However, the unsquared version, I think, is useful in a per slope effect size to talk about what that slope brings to the table uniquely, because that's directly tied to the interpretation of the coefficient. So for individual slopes, I think a partial correlation is a useful thing. For individual slopes, I also think Cohen's d. And by the way, I have partial in here in a few spots in my code and in a few places. It's just to remind folks that Cohen's d is part of the partial family in terms of what it means. It's the group difference relative to what's left. So putting them on one slide to compare, the denominator is the difference here in terms of the two. So semi-partial is out of total, partial is just out of that. So this was the pie analogy. Do you remember that? Yeah, like if I make a pie, hypothetically, actually I'm just going to go to Costco and buy a pie because they have pies that are like the size of a car wheel, like a monster truck wheel for $5. So I go to Costco, I buy a giant pie, I take it to a potluck, people eat half of it, I bring the other half home for my family. And if someone eats half of what's left, how much pie did they eat? Half or a quarter? If you think they ate half, that's a partial version because they ate half of what's left. But if you want to know in an absolute sense how much pie did they eat, it's a quarter of the pie. Question?
Where you would report the interaction along with the error remainder to get that partial eta squared or no?
What do you mean by interaction?
So looking, well, the C looks like the overlap of x1 next to the in the diagram.
Yes. C is the part of x1 and x2 that is also related to y. Yep, yes it is.
So, you know how we did A was like only x1, not the overlap area, but C is the overlap, would you go take bigger no? Like C over C plus B. Would you ever
Oh.
of that nature? To say that, you know, the interaction out of the interaction plus one remainder.
C over C plus E.
Yeah, I just, that's just a curiosity because it is a unique area, that's like unique to X, unique to X, but unique to.
I think it's theoretically possible to compute something like that. I can't think immediately off the top of my head how I would do it. I don't know how. I'm just trying to think, like, how would I isolate that? Let me think about that and get back to you if I can think of a solution for that. But I think theoretically, yes. You can do anything you want that would be useful. So how would we use these things? This is the example I did with the Pearsons. We don't need that. Let's go. This is the example we're going to walk through today with code and output. Do you want to look at the code and output rather than the results? Would that be more efficient? We like numbers. I have sort of a general strategy of like walking through concepts with example numbers and then showing you how I got them, but I feel like at this point in the semester we might be able to skip a step. Just look at the code and the output. Maybe? Do we care? We can look at the code. So this is example 4A that I have. I had posted 4B for today as well. I'm not sure if we'll get to it, but we'll see. This is the last time you're going to see the general social survey data, I promise. In an example, the last time we're going to predict income from variables like working class, age, and education. So I have two models in here to illustrate, I would say, like the simplest case in terms of how you would build a model that has multiple predictors in it and report effect sizes, and then a more complex model to show like what the extra layers of complexity could be in terms of doing the same thing with more complicated predictor specifications. So the data creation steps, you've seen all of this before. They're just all repeated here because each handout I make, I try to make it stand alone. So the first simple model is going to use a linear effective education centered at 12. It's going to have a binary version of marital status as a binary predictor. The complex model is going to have working class as 3 different categories, so we need to create 2 different contrasts to differentiate those. We have a continuous measure of age. We're centering at 18 as the sample minimum, as my choice. And then the same piecewise model for education that we've seen a few times, where we have 3 different slopes going through the different regions of education. And the same stuff in R. So are there any questions from either software package about how to make variables, how to recode things, center things, that kind of stuff? Are we feeling fairly comfortable with that at this point? Maybe? Okay. Yeah, these are fairly straightforward transformations. There's more complex kinds of data manipulation that's required in like 2-level or 3-level sampling design. So we get off kind of easy in this class, relatively speaking, that the data manipulation steps are not quite as involved. So here's a table summarizing what's going to happen with respect to sums of squares for each predictor when it's by itself versus what happens when they're put together in the same model. So we have, if we have an empty model, then there is no sums of squares effect because we haven't predicted anything, and we have a 0 R-square. If we put in linear education all by itself, its R-square is 0.148. So semi and partial give you the same information because there's nothing else that it's relative to. There's only one predictor in the model. The same is true if we put in binary status all by itself. Then partial and semi-partial are the same. And if we put them together, then this is what we would think happens in terms of just the straight sums of squares being added together, but that's not what's going to happen because these two variables are a little bit related. So that C part is going to have a contribution that we don't actually get to observe. So here's our model, beta 0, beta 1, beta 3. I have, let's see here, I have output in both programs. Which one do we want to look at first? R. Zoomers, what do we vote for? Zoomers said R. R from the Zoomers as well. Okay, R wins. We'll go R first. All right, so my formula then looks similar to what we've seen up to this point, now with just a couple different predictor variables in it at the same time. First question, do I have a significant model? I think so. P is less than 0.0001 for my F test. What is my F test testing? And don't say the model because I already used that one. What does this p-value mean? What is this? What is the question that's being answered that it's significant? What do we think? Here's a hint. What does testing the model mean? If you had to explain it in more specific terms. Michael, you want to help him out? Yeah, I'm calling on you.
Yeah. How well does your model explain the variance that's inside of your information?
Yeah, how well does the models...
Or fit? Or how is it fit?
Yeah, fit is...
I know.
Yeah, I'm not going to use that word.
Use of fit.
Yeah, that's a tricky one. Fit means a lot of different things, so I avoid that one. Yeah, so we can think of it two different ways. Is the model significant? Like, that's a shorthand way of saying, did we significantly explain variance in this outcome? Or said even more simply, is the Y that this model builds significantly correlated with the real Y, the observed one? That's what we're asking. And to build a predicted Y, this model requires one fixed intercept and two fixed slopes. So we're asking whether the end result of the model significantly correlates with the outcome. Not what happened for each predictor in building their contribution, but what happened in the end. So this is like the highest level sort of answer in terms of what you would want to know. Do these predictors work together in such a way that the prediction they create for the outcome is significantly related to the real one? And if it's significantly related, which it is in this case, a logical follow-up is how related is it? So this number right here is in an R-square metric, not an R. So it doesn't directly answer the question. But if I take the square root of it, then I can answer that in a correlation metric. So 19% of the variance in income is attributable to linear effective education and binary marital status. That's what this is telling us. Now, what is the contribution of each would be the next layer of concern. So my intercept, 11.47 is the predicted income level for what kind of person?
A high school graduate that is not married.
A high school graduate, because that's when this is 0. That is not married, because that's when this is 0. Yep, so this is something like the start of your results section would describe who the reference is for the model, and then you can talk about what happens to the prediction relative to that point. Very good. What happens if you have higher levels of education to your income?
For every additional year of education, you make $1,773.80 more.
Very specific answer, yes. For every additional year of education, you make 1.7 some odd $1,000 more according to this. And I would label that as significantly positive. 11 standard errors away from the null hypothesis of 0, so really unexpected. You would not see a slope this large if the true slope were 0 very often. If the true slope were 0 is the catch-all. Mm-hmm.
So is that still true is that relationship still true if you were in the married category then, I guess?
Ah.
Is that slope still applicable for education?
Great question. And foreshadowing what the next unit's going to be, actually. This slope is controlling for marital status. So we would say after adjusting for the difference between married and unmarried people, this is the unique contribution of education. And we would talk about this one in the opposite way. Now, I think your question was, does this slope apply equally to married and unmarried people? Now, that to me sounds like a research question, right? Like, is the effect of education the same in this group as it is in this group? According to this model, the answer is yes. There's nothing in the model that would allow for married and unmarried people to have a different effect of education. Yet. Can anyone guess what would be required to allow the effect of education to differ by marital status? Have you seen such things before?
Instead of a linear relationship, a quadratic relationship?
So quadratic. So for education, you could have a quadratic slope, like that's possible because it's a numeric variable, but that would not change the slope of education differently for married and unmarried people. It would just make the slope bendy. I don't know if folks is going to guess this, but oh, we just got an answer in the chat. Ding, ding, ding. Yep. What would do this? Let's see if can I type in here? Yes, I can. It will end up being a term that looks like that. That is called an interaction term. It is literally the two predictor variables multiplied together to create a new variable. You don't have to physically make the variable in this software. You can enter that term into the code and it figures out that that's what you meant. Yes, interaction effect, good Zoomers. The word moderation is what this gets at. So is the effect of education moderated by marital status? A term like that would allow that to be the case. So that's the next layer of complexity that we're adding in the next unit is interaction terms to see if the effect of the predictor is the same for everybody or whether it varies systematically as a function of your standing on one of the other predictor variables in the model. Lots of research questions are phrased as moderation questions, but that's not today. That's coming. Good questions. What about if you're married? What happens to your income? It's higher. So if you'd like to be richer, go find yourself a partner. Problem solved. How's that for causal inference? Yep. People who are married make $5.6 thousand more than people who are not married after controlling for education, is the way that we would phrase that. After controlling for or adjusting for, that's what unique means, is shorthand for that. So we've learned that both of these effects are positive. Both of these effects are significant. We've also learned that together they account for 19% of the variance in R square. Or that sentence was word salad. Help me fix it. What does this number mean right here? I'll pretend I screwed up on purpose. What's this number mean again? This is my R square. Maybe I should start throwing candy at people.
Proportion?
Proportion of,
I could total variance,
total variance, proportion of total variance, there we go, we're working together across the modalities here. Yeah, 0.19 of the total variance has been explained by the linear effect of education and marital status. We know both of them are significant, but we don't know which one did more work in building this level of prediction. So that's the next question. Oh, too far, too far. So for something like this, I could report a semi-partial R square to talk about the contribution of each variable to the overall. I could report a partial R for each one to talk about their unique contribution. Those are my choices. So for each of the slopes, I've added these effect sizes in Cohen's d and partial R metric that talk about their unique contribution. I could also have computed semi-partial R squares, and I did that actually in the example from last year to talk about the contribution of each of these. And I think that, yeah, I have that in the Stata output. So in this case, I have to go back up to Stata for that one. Stata has a command called pcore that spits out correlations in R squares in both the partial and the semi-partial metric. So you can use this function to get any combination of these you want, and doing so gives us the answer that, so 0.19 is how much the total R square is, 0.14 is due to education, 0.04 is due to marital status, and the rest, it would be like 0.01 or so, that's due to the common area C, the overlap between them. So it looks like education is much stronger of a contributor to the model than Mary. So these values then are directly comparable even though the slopes are on different scales. We can talk about the contribution to the model in a standardized way. Okay. So it's then Stata folks. I don't want to leave you out. Your output is basically the same, just a little bit organized differently. There's my F for the model, there's my P, there's my R square. Then we have our table of fixed effects. The only difference is that the fixed intercept is last. To do effect sizes, so all this work is what I did behind the scenes in R and building functions so that you wouldn't actually have to code all the math. I can't figure out a way to do functions in Stata yet. I have not learned that trick. I've been focusing on R. So I have a workaround in which these things are done somewhat manually, but the good news is that this code should be portable for the most part. So to compute effect sizes, essentially to add them to this table, that's what I'm trying to do. I have to save the results of the model to an object. So matrix is the command that does that. Matrix list then prints that object. So this table then is what is stored internally in Stata to access like these save results here from this. So what I want is to compute a D for marital status as the effect size that is for groups, since this is a binary predictor. To do that, I need this T value and I need this degrees of freedom. So rather than enter into the code these numbers specifically, what I'm doing is telling Stata to go to this spot in the saved output and use the saved information. That way the code is recyclable. So the formula for Cohen's d is 2 times t divided by the square root of the denominator degrees of freedom. So in here, that's row 3, column 2. So that's going to get me to that number. And this is row 7, column 2 to get me to that one. And so then the result is computed from this display command and printed in your output. So d is 0.46. I don't have to do this for all the other partial r's and semi-partial r's because I have pcore as a separate command that will do that for us in Stata for variables in which you only have one slope for the predictor. Okay, so putting it together, in the simplest case, there's really no way to screw this up. You can use semi-partial r squared to talk about the variable's contribution to the r square, or I would recommend partial r to talk about the unique effect of each of these slopes. The one that gets tricky is partial r squared, because people want to talk about that as the contribution to the r squared, and it's just not. That's not what it means. So to avoid that temptation, I stay with r for partial. I switch to r squared for semi-partial. All right, how we doing, folks? Now the rest of this gets a little bit tricky. Let me head back to the slides for this one because I got to set up the story a little bit. So this was the equation we landed on, left with on Thursday, I think, and I pointed out that if I showed this on day one, you people would have been very scared. But now it's nothing, right? We can handle this. This is just your typical, you know, like 7 predictor model, no biggie. Right? She's like, we did this, we've built this in pieces, right? That's what we did in the last example is we did the working class variables in one model, we did age in a second model, and we did piecewise education in a third model, so now we're putting them all together. So here's what's going to happen in terms of the r squared for the separate models versus joint. If I were to combine the results from the separate models, that creates a predicted r square of 0.38, but what it's actually going to turn out to be is only 0.29 because these predictors have overlap. So I have effect sizes here in semi-partial and partial r squared. So for instance, working class, together, these slopes generate a semi-partial r squared of 0.04. So the 0.28 is the r squared. The contribution of that from these predictors is 0.04. Likewise, the contribution from the age predictors is 0.08, and education also had a 0.08. The partial versions are relative to what is left that wasn't taken by the other predictors. So that's the one that's trickier. So in this model, it's going to be a little bit tricky to think about effect sizes for each of these slopes because they're designed to work together in the cases of, in each of these cases, for instance. So for working class, beta 1 and beta 2 share a common reference of low. So that means that they're somewhat redundant. So we can't just look at the semi-partial r squared for this one and that one and add them together because we have to account for the overlap between the variables. So that's, we wouldn't want to do that directly. Age, this linear slope is not the slope of age period. It is specific to when the interaction term, this quadratic here, is 0, which means it's at age 18. So the age slope that I get on my output is really only one of an infinite number of possible slopes along that curve, right? This is the U, the sad face version, where the middle-aged people are the richest. Like if you go up from 18, it's positive, and as you get to the top, the slope is 0, and as you get over here, it's negative. Each of those potential slopes would have a different effect size. But it's sort of weird because this is a lower order term that this one needs. So it's like, I wouldn't necessarily make anything of it. Really what I want is to lump these two together and get their effect size. And the same thing is true of education as was true for working class. Because these have some commonality, I can't just add their effect sizes together to get some kind of total. So we'll have to work a little bit harder in these cases to get an effect size that takes the slopes together without just straight adding them up, because that's not allowed. So I will show you how to do that. So here's an overview of how to get effect sizes from different software packages. In Stata, P-core is semi-partial and partial R's or etas in eta squares. You can also get an f-test via a command called test. I'm going to introduce that today as well. And there's also a really cool command called nestreg that I'll introduce in the next example that can fit multiple models and compare them. In R, I found a package called ppcore that will do something very similar. It will only work for single slopes, just like Stata though. And I found a couple different things in R that will allow us to do hypothesis tests for groups of slopes however we want. So I'll show you how to get all of that kind of stuff. This is the overall process though. So this is the process I will show you. Step one is to figure out what the overall model sums of squares would be, and the leftover part, the residual, and get the total overall that these things would sum to. Then we estimate a model without the term we're trying to get the effect size for, so we can see by how much the sums of squares goes down. That is known as SS effect here. So it's like, by how much did you harm the model by taking this thing out? That's what we're trying to capture. Then you can compute effect sizes for the contribution of that slope or slopes by comparing the change in the sums of squares to the total. And so we have the semi-partial version here, or the partial version that's relative to residual. So this is how you can answer questions about effect size and contribution from one model. Essentially, like you fit the model you want, you take something out to see what happens, you take something out to see what happens, rather than doing it sequentially. Because if it's sequentially, you have to defend your order. But because that is more common, you get a chance to practice that in homework 4 as well. So let me get out of here. I'm trying to, at least. Okay, so that's the story I had to set up. Here's the process. So do we still want to do R first? Yep, we'll do that. Okay. Come down, skipping ahead. Okay, I'm on page 7. So reviewing these things here, these two variables are for working class. They indicate how the middle group differs from the low group, how the upper group differs from the low group. Then we have a linear slope for age, when age is centered at 18. And we have this thing. What on earth is that? Here's your clue. Unhappy face. Yeah, this is how you make a squared variable in R. So the caret 2, you'll see that in a lot of software packages that squares things. And then you put the I outside this to avoid like it would interpret this literally somehow and screw things up. So this I is called an inhibitor that stops that from happening. So this is a very roundabout way of saying age squared. Then we have the 3 slopes that we created for piecewise education. So in the results, we have a significant model. How many slopes did it take to build this level of prediction? 7, yeah. And I know that because this is this. So this is an overall test of all 7 slopes at the same time being 0. That's what we're asking. F provides a test of the contribution per slope on average relative to the expected contribution for some random slope that's not yet in the model. This is my R square. So 0.29, 29% of the variance is explained by my model. If I take that R square and unsquare it, then I can talk about the correlation between Y hat predicted by all this stuff and the actual Y that's in the data set. Let's practice. So I see I'm laughing. Do you know why I'm laughing? Because I see some weirdness. My intercept. Anything strike you as odd about that? It's negative. the expected income level of my reference person is negative $3.6 thousand. Who is that person? Let's go down the list. When are these zero? Yeah, the low group, given my coding scheme, I set them as the zero. When are these zero? If you're 18. And when are these zero? You might remember. Same coding scheme that we had used for this in the past. Remember who the reference was? It was 11th grade. Yeah. It's not in the names, so that one's harder. And now you see why I name things the way that I do, to try and keep the reference like as part of it. So when I write these things, like whoever is the zero is the first letter and whoever is the one is the second. That's just my own way of doing things. So it's not that zero is a weird, non-possible value, right? You can have someone who labels themselves as working class because they're or lower class because they're 18 and they have only an 11th grade education, right? That person could exist in my sample. So the fact that this is negative likely points to some kind of model misspecification. The predicted value for that reference person who can exist is nonsensical. So that either means I might need a different kind of model, meaning that I would need a model that understands that you can't predict negative income and shuts off the predictions at zero. That would be an example of a generalized model, which is regression models for not normal outcomes. They build in extra guardrails. So like logistic regression is an example of that. If you have a binary outcome, count regression builds in a guardrail such that you can't have negative predicted counts. This would be like the same type of problem that would be avoided here. But it could also be that what I have right now, each of these has an additive combination, not a multiplicative one. Additive means that I'm assuming that these group differences hold no matter how old you are and what education you have. And I'm assuming these age differences hold no matter what group you are and what education you have. So to the extent that these are not additive, that they are actually interactive, that can result in model misspecification. But I thought 7 slopes was enough for one model. We'll do interactions in the next unit. But this should worry you when you see this. Like if your intercept is for someone who can exist and it's impossible, that points to a likely problem. But we'll just ignore that for time being. Do I care that it's almost significant? Is that something I would include in my report? No. That means that it's almost not different from zero. And at the intercept, we don't usually have that as a point of reference. What do these tell me? They're positive. They're significant. Working class is a significant predictor. Who's higher? If the low group is the 0 and the alternative group is the 1 here. Is the low group or the alternative group higher in each of these if the slope is positive? The alternative, yep. So in your homework, I've given you a couple different chances to practice this. A couple more are coming. In order for the slope direction to be correct, we have to talk about it as how the alternative group differs from the reference. You can't reverse it, otherwise the slope would be negative instead. So the middle group is higher than the low group by 6. The upper group is higher than the low group by 7. Do we know the difference between middle and upper? It looks like about 1.2 to me. Is 1.2 significant? We're gonna have to figure that out. That's a linear combination though that we can ask for separately. No worries on that one. We'll do that in a second. So after controlling for age and education, these are the group differences attributable to working class, self-reported. These two. For every year older you are, income goes up by $1,000. Correct or incorrect? It's like, it sounds like it could be right, but she's asking me, so that must mean it's wrong. You're shaking your head? Zoomers, what do we think? What do you mean by start by? Yeah, I think you're going on the right track. The zeroing, Yeah, so I'm going to make my parabola again. Here we go. That's a better one. Where is the slope at? Which, is it at this elbow, the top, or this elbow? You can make it a multiple choice. Yeah, it's over here. Yeah, so this is only the linear slope of age when this term goes to 0. That's the squared version. So this is the slope at 18 specifically. So it is still the expected difference in income per year of age, but at 18, because that slope changes as you move up the parabola. So yes, start point. I like it. Where the variable starts, I centered it at the minimum on purpose, then that slope is positive at 18. Now, what happens to it as age increases further? Do you remember the rule?
Decreases times 2.
Times 2, times 2. If you don't take anything else away from quadratics, just remember the times 2. What ends up happening is that this term, this slope of the squared term, is called the quadratic slope. It is half the rate of acceleration. So to talk about how the rate of acceleration operates on the rate of change, so to speak, using physics terms here, we have to multiply it by 2 because it's only half. So this positive slope, I would say, becomes less positive or weaker by 2 times this number per year of age. And that is also significant. So as we move up my arm here, right, it's becoming less and less positive. Eventually it hits 0, and then it flips over to negative on the backside. And you can compute the point at which it flips over as well. Aperture, I think there's a word for that. There's a couple different words for that. Okay. These three, these are all linear, but they apply to different sections of education. So this one tracks the difference in income per year of education up until 11th grade. So for every year more educated you are up until 11th grade, your income is predicted to be $250 some higher, but non-significantly. If you go from 11th grade to 12th grade, your income is increasing by about $3,000, and that is p-value of 0.07, marginally significant, approaching significance, it's trending. Just come back later and check on it, you might get there. 1.5 is the benefit you get from each additional year of education after grade 12. And that is significant, thank goodness, or we'd all be in the wrong spot. So I can compute partial effect sizes for each of these things and talk about them. But what I can't do is try to add any of this stuff together because of the overlap. So I want to show you how to do that concept of adding these two slopes together to get a joint effect size, but not literally adding them together. So extra pieces of information then. This stuff all shows up by default if you run the code. Now I got to do some extra work. So first thing I want to know is the missing group comparison. I want to know if the 1.2 that differentiates the upper group from the middle group is significant. So that requires a linear combination like this. Why is this so long? Because there's 7 slopes. What happens if you put in the wrong number of zeros and ones?
Ew.
It yells at you. Okay, so it's looking for one number in every spot to fill in this matrix equation. And if you don't have a number in the spot, it's going to yell at you. How do I know where to stick my zeros and ones? What's the order here? It is the order in which they show up in this table, not necessarily the order in which you put them in your model. Okay? I found this out the hard way many times in building examples because I like to set up my model so that I have like the stuff that was there before and then the new things are at the end. And there's times where it reorders the new things to be in the middle because it's following whatever internal system that it wants to do. So just double check that your output is in the order that you had intended. So what I'm trying to do is get the difference between these two slopes. Therefore, in the zeros and ones, I put a -1 for the medium slope. I put a 1 for the upper. And this translates into upper minus middle. And that's how I get my 1.2. 1.1484. My math is a little bit off. I hope you can forgive me. Is there a significant difference between the middle and the upper groups? How do I know? Yep, right here. This slope of 1.14 is like a half a standard error away from the null hypothesis of 0. So it's well within expected territory, not outside the boundaries. Said differently, its confidence interval overlaps 0. Now, what if reviewer 2 comes at you and says, the reason you don't have significance is because you have too small of a sample. You don't have enough power. Would they have a point? Maybe. What's power again? Like, oh, it's a good thing, right? Like type 1 error sounds bad and power sounds good, so let's start there. Those are two different things, by the way. So type 1 error is the probability of a false alarm. You thought you had something, but actually you don't. Type 2 error is the opposite of that. You missed. There was something there, but you didn't see it. So power is the inverse of type 2 error. So if type 2 error is the probability of missing, power is the probability of not missing. So if my type 2 error rate is 20%, my power is 80%, and that's what we want it to be. So conventionally in the social sciences, we are taught to aim for an 80% power rate, which translates into a 20% miss rate. So power is the probability of finding an effect that is really there. So reviewer 2 says, the issue is that you have too small of a sample and too low a power, and that's why this is non-significant. How do I rebut that? Or address it at least? Have you had to practice this yet? I know many of you, this is your first year. Have you had to deal with reviewer comments before in manuscripts? A few of you should nod. Hillary, you should be nodding. Is reviewer 2 a kind and gentle soul, usually?
No, they are
No.
heartless and ruthless, and they're there to tear you to shreds.
That is correct. I am part of a Facebook group called Reviewer 2 Must Be Stopped, in which people complain about reviewer 2 comments and things like that. So it used to be reviewer 3, but most journals can't even get 3 reviewers anymore, so it's reviewer 2. So responding to reviewer 2 and reviewer 1 is something we're going to have to learn. And it always follows the same formula. First off, apologize, even if it's not your fault. If it's the fact that they didn't read, then you can say that we're sorry that this was unclear, right? It's my fault, not your fault. I know you didn't read a word I said, but it's because it was unclear, and we're sorry about that. Then you can explain what you want to do. It's like a compliment sandwich. Apology, explanation, and then thank them for their valuable feedback as the other half of that. So reviewer 2 makes an excellent observation, and we apologize for failing to consider the implications of sample size in describing the results of our model. Okay, there's my apology. Now, what am I going to say? Well, I missed the effect. But what effect was I trying to find? This is where effect size comes in. So I have a non-significant effect. That either means I have a large effect with very little power, or I have small effect. Here's the Cohen's d and partial r effect sizes. I have a standardized mean difference of 0.03. 0.03 standard deviations apart. Do you think that sounds like an effect that's worth finding? I would say no. I'd say I don't think it's a power issue. I think there's nothing to be found. And that argument is supported by providing effect sizes. Likewise, if I wanted to talk about something marginal, even though it's not significant, I would refer to its effect size by saying, hey, at least this effect size looks somewhat decent. For instance, that one is 0.13 standard deviation units, or a correlation of 0.07. Okay, yeah, not that exciting. But we thank them for their valuable feedback. That's the end of that. So that's not significant. Now, how do we get the effect sizes for the joint combinations? I built you a function in R to do this. So it's relatively straightforward because there's a super easy function in Stata that does the same thing, and I wanted to be fair. So the objective here is to find out, as a set, what is the contribution of the working class slopes? Like, let's get an effect size for those. What is the contribution of the 2 age slopes? And then what is the contribution of the 3 education slopes? So I'm grouping these so I can talk about the contribution of the idea to the model and not just a specific slope. So first, fit a model without the terms in it that you're trying to get the effect size for. So for here, I took out the 2 group variables. Then I made a function. It is called r squared change f, because that's what it computes. I want to tell it what is the reduced model, meaning the one without the 2 predictors that I care about. What is the comparison model that had everything in it? So that's model 2. And what do you want to name this thing on your output? So I named this working class because those are the 2 slopes that I took out. So then my function compares the results of the big model to the lower model and spits out those quantities. So overall r square is 0.288. We learned that already. The part of the r square that is attributable to those 2 slopes is 0.04. So it's not 4% of the 28%, but just that's the amount of the r square. So if I had a model without those 2 slopes and then I added them back in, this would be the net change in r square. Uncoincidentally, the same number is out here in the semi-partial r square column because that is what it means. So I labeled them that way to be crystal clear. Semi-partial r square is the amount of the r square that set of predictors is responsible for. That is the same thing as how the r square would change if you added them to the model. Same idea. So I can test this change in r square for significance as well. So I have 2 slopes that I'm using for that. Denominator degrees of freedom is still from the overall model, and that results of an f for the difference of 21 with a p-value that is 0 to many, many decimal places here. So yes, in addition to the overall model being significant, the joint contribution of those 2 slopes is also significant, and it's responsible for 4% in terms of the r square. So that's how, for multiple slopes at the same time that need to work together, how we would get effect sizes for the set, is to do a model comparison instead. So I repeated that down here for age and then for education.
So can you reiterate that R squared change that is out of the 0.29, 29% that is accounted for by this model,
Mhm.
that's how much those slopes contribute to that, or that's out of the total?
So the full model is this. This is the contribution of those two slopes to this.
Okay, yeah.
Yep. So they got 0.04, that means there's 0.24-ish that the others did. The others or the joint. Question?
Could you think that also as above and beyond, because those two could have been, had some interaction that would have some variance that they could have come from them, but was already there, that was accounted for with other variables?
That 0.04 reflects the unique contribution of those two variables above and beyond what's already there.
That's just unique.
That's unique. So I did the same thing for age, where I took those out of the full model, and it looks like age is responsible for 8% of the variance that's explained. I have to be careful. I keep wanting to avoid the word of because it's not a proportion of a proportion. That's the other class. So 0.29 is the total R square. 0.08 is the unique contribution of age. And likewise, 0.08 is the unique contribution of education in this case. So these numbers do not add up to the total. They're close. 0.04 plus 0.08 plus 0.08 is 0.2. So where's the rest? In between them, area C in the Venn diagram. So there is about 8% of the variance that is explained by more than one of them at the same time. We don't know which. But that goes into the R square. So state of folks, I don't want to leave you out. That's model 1, we want model 2. Okay, so here's model 2. For squared terms and interactions in Stata, the code is a hashtag or a pound sign, depending on how old you are. So this directly adds the squared variable without having to physically make it in the data set, which is advantageous. All right, so here's the model results from that. I was on the wrong one here. Here it is. So F, R square, p-value, same as usual. Here's the table of coefficients that we just walked through. This is me then saving and accessing stored information to compute stuff. So I am going to be somewhat manually computing these effect sizes. So I need the residual sums of squares from the overall model. I need the, what's that one? That is the model sums of squares as well. And I'm going to save those two numbers as variables. So this is the same logic that R uses in terms of saving results as objects that you can then access and do math on. So SS residual is now like a programming environment variable that holds this number. That way I don't have to physically type the number every time. Same with SS full. Oh, that's what this is. Okay, yeah. Got it. So I can get partial and semi-partial effect sizes per slope that's in the model, but these are the ones that I would not try to add together to get some kind of combination. I can get individual effect sizes using LinCom. So this is the slope comparison. -1 and then 1 creates a difference in the two slopes. And then I used saved results to print various kinds of effect sizes down here. And then here is how you can get a joint hypothesis test of any slopes in your model that you wish. This is a new thing in Stata. So the command test. In separate parentheses, you tell it what you want to happen to the slopes. So this is a really flexible routine that allows you to do whatever you want, essentially. In this case, what I'm trying to do is say, what if these two slopes were in the model? How much worse would it get? And the answer is significantly worse. So this is the same information that I just showed in R that my function built in terms of F tests and R square change that goes with them. So in Stata, we can do the F part separately, and I'll show you in the next example how to easily get the F and the R square at the same time. Likewise, here's one for the overall effective age, and then here's one for the effective education. So in each of those cases, those make a significant contribution. What it would then be is the same process here of rerunning the model without that term in it to get what the new sums of squares would be, and then computing these effect sizes. So this code you should be able to just borrow because it's tied to saved results rather than specific numbers. So I did that to get the same effect sizes as we had in R. Ta-da. And in case you're like, oh my God, that's a lot, here's some words. So this is the type of result that I would provide. So for instance, this is a table of the fixed effects solution as it is known. I want to point out a couple things. I don't have all the columns in here. You don't need them all. I have estimate and standard error. I don't have T. Why don't I have T in here? Like if you look at there's a whole bunch of stuff, right, that I could put in here, and I'm not putting it all in here. So my question first is, why don't I have T as a column? Well, each of these slopes would have a t-test statistic for it. I'm asking, like, why don't I report that information? How do I build t? Do you remember the formula? It's a ratio. It's this divided by that. So they can build t if they want. T is only a means to an end to get p. So I gave them p. I don't like stars. I don't like that. I'd rather just give them the full number and let them decide what to do with it. You are allowed, by the way, to not have leading zeros on any number that doesn't go above 1. So I can save some of the visual clutter in the table. And note that I'm saying p less than, so that I can report 001. Here's my two effect sizes. So in the table then, this looks mostly like this fixed effect solution with one exception. This line right here. That was not in the fixed effects. That was the extra thing I asked for, but because it's relevant in understanding the whole story, I put it in here. So I put it in parenthesis, and the note says model implied effects are given in parentheses that were computed as linear combinations, and I also clarified how I got those effect sizes very specifically in case anyone wants to know. I would like to also contrast. Look at the names in my table. Do you think a random reader is going to want to read these names? Nope. Don't do this to your readers. Give them proper names. Don't use the names of the variables. So I have relabeled things in such a way that they should be more interpretable as to what those actually mean. And then here is text describing all of the results. And that's it. We made it. So the advantage of fitting one model and then taking things out of it to compute effect sizes is that your results don't change based on the order in which you added things. Like age has a different effect size when it's initially added than when it is in combination with other things. To avoid the ambiguity as to which is the right one, having everything in the model at the same time to assess effect sizes solves that problem. So that's not the most common approach. Sequencing the models is more common, so in the next example, I will show you how to do that too. So example 4B that we'll get to next time is meant to be like a big recap, and it's on a new data set, so we don't have to talk about income anymore. Fair? She's like, I'm done. Have some candy, you'll feel better. All right, 312 folks, thanks for being here. Any questions before we adjourn? No? Okay, take some more candy with you. I will see you on Thursday. Go vote if you haven't done so. Bye for now.